All right. Okay, sound seems to work. There we go. Right. So we are back. We are back with another live stream. Yesterday we were looking at message passing neural networks that operate on graph data. And yeah, just give me a second. Turn on the lights. Today we want to look at subsequent work published in the space of graph neural networks and graph isomorphic networks. Let's quickly summarize what we learned yesterday. And for that, we can go back to the paper that we read. So the paper we read yesterday was called Neural Message Passing for Quantum Chemistry. And they were summarizing the literature on graph neural networks into a common framework, a framework they call message passing neural networks. And the basic idea of message passing neural networks is that obviously they operate on graphs, and you can use them as a graph mapping function that is an invariant to graph isomorphism. So graph isomorphism is the concept of two graphs being essentially structurally the same, but maybe the vertices are mapped a little bit differently, or they're kind of turned around, but the edges are still intact. Yeah, and they introduced this framework with the message function, the vertex update function, and the readout function. And they were testing it on the QM9 dataset, which to predict some properties about molecules. So I would say some of the more relevant subsequent work in the realm of graph neural networks is the paper published by Xu, I don't know who, Leskovec, and Stephanie Jagelka. I don't know, Stephanie, probably, right? From MIT and Stanford. And this was published at ICLR in 2019. Right, so the title is How Powerful Are Graph Neural Networks? I haven't read this, I haven't read the abstract, I haven't read the introduction, I didn't read any of this, but I think this is one of the more relevant work related to graph neural networks. Subsequently, one of the more important works on graph neural networks that is subsequent to the one that we were reading yesterday. So I would say, again, the first step when reading the paper is obviously starting with the abstract, introduction, and the conclusion, as well as the structure, related works, and references. All right, so this is the first thing we're going to do, is that we will start reading the abstract. We will read the introduction. We will look at how the paper is structured. We will not look at the equations for the first pass. We will look at the conclusion, which is not that much. We'll look at the references, and I wonder whether we find the paper from yesterday in here as well. So this was neural message passing. Maybe we find that. This isomorphism. Presentation on graphs. The references. Learning I also don't remember the first author. The first author was, where was it? Oh wait, I have it open, right? I have it open here. Neural message. Yeah, they have it. They have it here, of course. That's good. So it builds on this. Okay, so let's start by reading the abstract. So how powerful are graph neural networks? Graph neural networks, GNNs, are an effective framework for representation learning of graphs. GNNs follow a neighborhood aggregation scheme where the representation vector of a node is computed by recursively aggregating and transforming representation vectors of its neighboring nodes. Many GNN variants have been proposed and have achieved state-of-the-art results on both node and graph classification tasks. However, despite GNNs revolutionizing graph representation learning, there is limited understanding of their representational properties and limitations. Here, we present a theoretical framework for analyzing the expressive power of GNNs to capture different graph structures. Our results characterize the discriminative power of popular GNN variants such as graph convolutional networks and graph SAGE, and show that they cannot learn to distinguish certain simple graph structures. We then develop a simple architecture that is provably the most expressive among the class of GNNs and is as powerful as the Weisfeiler-Lehmann graph isomorphism test. We empirically validate our theoretical findings on a number of graph classification benchmarks and demonstrate that our model achieves state-of-the-art performance. Okay, again, they have this concept, the concept of the graph is at the very center of it. And what the neural message passing network also is introducing is this concept of aggregating messages from neighbors. So let's say we have vertex 1, we have vertex 2, and vertex 3, and vertex 4, and they are all connected to 1. Now, maybe you also have a vertex 5 here for this. And what the message passing neural network now does is that what the message passing neural network node does is it goes through all of the nodes. Oops. It starts, for example, with V1. It has a hidden state for V1 at time step 1. It computes a message for this, which is the so this was, we had this over here. The message function. So it computes, it looks at all of the neighbors. All of the neighbors of V1 are V2, V3, and V4. And each of them have a hidden state, HV2, HV3, HV4. And for each of them, they apply a message function of HV1 with all of the neighbors. And they sum them up to a message of V1 at time step 2. So this is the message function. The primary mechanism of communicating states between nodes. And then they have the vertex update function. And the vertex update function takes the message, so MV1, and it takes the current state of the node. They call it U, and they use that to update the state of V1 for the next time step. And they do that for all of the nodes, and then they do this T times. So in the end, you have HV1T, HV2T, HV3T. For our simple graph, HV4T. And what they then do is they put some kind of aggregation, which could be a set-to-set network, and they put this aggregated state, this sort of graph embedding, into another MLP, and then they get the output. And this they call the readout function. Okay, and this is what they basically refer to when they say that the GNN, where was it, aggregates by recursively aggregating and transforming representation vectors of its neighbor nodes. It is recursive because it's done like T times, the same thing, similar to a recurrent neural network, and it's always doing it on the neighbor basis. And we also saw that the message passing neural network they were using in the paper from 2017 here, they were using a master node that is connected to all of the nodes. So they had a vMaster here, and that's connected to V1, V2, V3, to all of them. And this, of course, because we only do it T times, if we have a very large graph, not all of the messages may end up at the relevant nodes. So if we have a very long chain, for example, and we only do these updates like 4 or 5 times, and our chain is 10 vertices long, then the message from vertex 10 will not reach the message of vertex 1. And they were using for this a master node, or they were using virtual edges So what they also said, okay, they used virtual edges so that everything is connected to everything, but they are separate from the real connections. Okay. Right. Like so. So this would be the virtual edge. I mean, this theoretically is also vertical, but whatever. Okay. So this is basically the summary again of what we looked at yesterday. Let's put that maybe here and a little bit smaller. Yeah. Okay, so introduction. Introduction. Oops. Learning with graph structured data, such as, wait a second. Learning with graph structured data, such as molecules, social, biological, and financial networks, requires effective representation of their graph structure. Recently, there has been a surge of interest in graph neural networks, graph neural network GNN approaches, for representation learning of graphs. GNNs broadly follow a recursive neighborhood aggregation or message passing scheme. So this is the reference. Nodes passing messages to other nodes that are in the neighborhood of the node. So here we have the concept of message passing. So each vertex in each round, if you want to say, passes on its state to the vertex it's connected to using its hidden state and a message function. All right. After k iterations, so this is repeated k times of aggregation, a node is represented by its transformed feature vector, which captures the structural information within the node's k-hop neighborhood. Of course, if we only have a k of 1, we can only get the information from each of the neighbors that are direct neighbors. If we have a k of 2, v1 will also capture messages through the state of v2 in iteration 2 of v6. So this is 2 hops, right? The representation of an entire graph can be obtained through pooling. For example, by summing the representation vectors of all nodes in the graph. So this is what they say. Okay, in the end we have HV1K, HV2K, HV3K, H, ... And we somehow have to aggregate them together. You can do a max pool, you can do an average pool, you can do sum, you can do whatever, you can do a set to set, as they were doing in MPNN, in the MPNN paper. And then you use this graph embedding, which results from this, to predict something about the graph. Right? Which is essentially the readout process. readout function or process or whatever. Okay. So many GNN variants with different neighborhood aggregation and graph level pooling schemes have been proposed. A lot of references here. Empirically, these GNNs have achieved state-of-the-art performance in many tasks such as node classification, link prediction, and graph classification. However, the design of new GNNs is mostly based on empirical intuition, heuristics, and experimental trial and error. There is little theoretical understanding of the properties and limitations of GNNs and formal analysis of GNN's representational capacity limit. So essentially what they are saying is, okay, we have so many different GNN variants. And it's basically a trial and error process of improving this. And we produce so many of these, right? Boom, boom, boom. But we want to do it differently. We want to take a theoretical approach. They want to take a theoretical approach. So what is the theoretical limit to the architecture? Sure. So what, in other words, what can I express with a given GNN architecture? For example, just by theoretically looking at the math, looking at the computation, can I already say that some things cannot be classified with this, or some things cannot be learned with this, because from its structure, it's already impossible from how it's built. And then maybe come up with something that might perform better and can do that by design. Now that doesn't prove that it is possible to learn this with stochastic gradient descent, but in theory it should. Okay, that's an interesting approach. They try to do it on a theoretical basis, and now we also already understand what they will do. So they will look at the GNN architecture. They will make some lemmas. What should this be capable of doing? They will then look maybe at some of the existing ones and say, okay, we can prove that this architecture cannot handle isomorphic graphs, isomorphism in graphs, for example. And then they will propose probably an architecture that can. And they will also probably show that their approach is effective by testing it on a data set. So let's continue to read. Here we present a theoretical framework for analyzing the representational power of GNNs. We formally characterize how expressive different GNN variants are in learning to represent and distinguish between different graph structures. So They test the discriminative power of a given architecture by looking at how well an architecture can distinguish between different graph structures. Our framework is inspired by the close connection between GNNs and the Weisfeiler-Lehmann graph isomorphism test. So this might be worth looking at. What does the... So this is something I lack the background in, right? What is the graph isomorphism? Test. Maybe we can read it, maybe it's readable, maybe not. But I think this is something we should do. So the test is probably okay. It's probably an algorithm to test whether two graphs are isomorphic. That is, the other one graph is just a mapping of the other graph where the edges stay the same. Okay. A powerful test known to distinguish a broad class of graphs. Similar to GNNs, the WL test iteratively updates a given node's feature vector by aggregating feature vectors of its network neighbors. Okay. What makes the WL test so powerful is its injective aggregation update that maps different node neighborhoods to different feature vectors. Our key insight is that a GNN can have as large discriminative power as the WL test if the GNN's aggregation scheme is highly expressive and can model injective functions. Okay, so injection is, okay, if x1 is equal to x2, then f of x1 is equal to f of x2, which is basically the thing that we're trying to test with graph isomorphism. And when the neural network is invariant to that, it should be this injective function. So we also have this concept of a GNN as an invariant to graph isomorphism, which is just a way to say this is a function that if two graphs are isomorphic, they will be treated the same. So if G is isomorphic to G prime, then our network model f of G is equal to f of G prime. Okay. Our key insight is that a GNN can have as large discriminative power as the WL test if the GNN's aggregation scheme is highly expressive and can model injective functions. To mathematically formalize the above insight, our framework first represents the set of feature vectors of a given node's neighbors as a multiset, i.e., a set with possibly repeating elements. Then, the neighbor aggregation in GNNs can be thought of as an aggregation function over the multiset. Hence, to have strong representational power, a GNN must be able to aggregate different multisets into different representations. We rigorously study several variants of multiset functions and theoretically characterize their discriminative power, i.e., how well different aggregation functions can distinguish different multisets. The more discriminative power the multiset function is, the more powerful the representational power of the underlying GNN. Our main results are summarized as follows. We show that GNNs are at most as powerful as the WL test in distinguishing graph structures. We establish conditions on the neighborhood aggregation and graph readout functions under which the resulting GNN is as powerful as WL test. Three, we identify graph structures that cannot be distinguished by popular GNN variants, such as the GCN and graph SAGE, and we precisely characterize the kinds of graph structures such GNN-based models can capture. 4, we develop a simple neural architecture, graph isomorphism network, GIN, and show that its discriminative representational power is as equal to the power of the WL test. We validate our theory via experiments on graph classification datasets where the expressive power of GNNs is crucial to capture graph structures. In particular, we compare the performance of GNNs with various aggregation functions. Our results confirm that the most powerful GNN by our theory, i.e. graph isomorphism network, also empirically has high representational power as it almost perfectly fits the training data, whereas the less powerful GNN variants often severely underfit the training data. In addition, the representationally more powerful GNNs outperform the others by test set accuracy and achieve state-of-the-art performance on many graph classification benchmarks. Okay, so what does this mean? They try to look at the representational power of a GNN. And they will do this by looking at the architecture and how the GNN architecture processes multisets. So multiset 1, multiset 2, and then we get a representation out of it. And for example, if those two are different, and those two are somehow the same, then we have a problem. Then the representational power is low, for example. Good morning, how are you? I mean, it's not really morning at in my time zone, but I'm fine. How are you? We are reading another paper on graph neural networks. Okay. So they try to formally or theoretically assess how well an architecture can represent a set of nodes. Okay. I haven't eaten yet, but it's almost lunchtime here too. Yeah. Then maybe grab something to eat. Okay, so how's this? Where are you? I'm in Germany. Where are you from? Oh, you were Spain. Nice. You were in Vienna. Yeah, Vienna is a very nice city. It's huge. Has a lot of nice buildings and beautiful city. All right, so how is this thing structured? Okay, preliminaries. So something about graph neural networks. You love the Opera, yeah? I don't exactly know what the Opera district is. Opera district of Vienna. We were also, I don't know if we looked at this, but there are several beautiful places there. Yeah. It's very great. It also has very good public transport and yeah, it's a nice city. I would say one of the nicest cities in Europe. Probably also to live in. Okay. So some preliminaries on graph neural networks, then a theoretical framework. So this is more or less their core piece, right? Not really. So their theoretical framework for assessing the representative power of a GNN. Then probably, yeah, then their core thing, the graph isomorphism network. And then the readout function. Okay, then some other things. Mean and max pooling. And other related work, okay. Then they have their experiments. They have a baseline, they have theirs probably. Then they have the conclusion. So let's read the conclusion. In this paper, we developed theoretical foundations for reasoning about the expressive power of GNNs. So, and proved tight bounds on the representational capacity of popular GNN variants. Oh yeah, I was on there as well. But not in winter. It was in summer. It's up. I can imagine that it's cold up there. Okay, so we also designed a provably maximally powerful GNN under the neighborhood aggregation framework. An interesting direction for future work is to go beyond neighborhood aggregation or message passing in order to pursue possibly even more powerful architectures for learning with graphs. To complete the picture, it would be also interesting to understand and improve the generalization properties of GNNs, as well as better understand their optimization landscape. Okay, so they have the theoretical framework. Which they establish. And this looks at a GNN and at its representational power. Okay. and which is basically, okay, how well can this thing process a multiset or distinguish between two multisets? Probably. Then they say, okay, the existing ones are not that good. Probably. Then they introduce their own. Introduce their gin. Do you have a new GitHub account? I think I renamed my GitHub account. And test it on benchmarks. And this sounds pretty reasonable how they do this. So let's look at the references. And they also say, okay, future work should go beyond oh yeah, okay, I probably because I renamed it. Future work is beyond message passing. And which they call neighborhood aggregation. Neighborhood. Is it this way? Yeah. And we can look at graph attention networks, which work a little bit differently, I guess. But that's for future. Okay, let's look at the references. So a diffusion convolutional neural network, graph isomorphism, interaction networks for learning about objects, relations, and physics. An optimal lower bound on the number of variables for graph identification. Library for support vector machine. Okay. Convolutional neural networks on graphs with fast localized spectral filtering. The Weisfeiler-Lehman method and graph isomorphism testing. So this might be interesting to look into, but okay. Convolutional networks on graphs for learning molecular fingerprints. Isomorphism of colored graphs with slowly increasing multiplicity of Jordan blocks. I have no idea what that means. A guide to the theory of NP completeness, okay. Interesting. Who were the... It would be interesting to look at the people who were at ICLR at this conference. ICLR 2019. Who are the guys that... There are probably different tracks, like the talks. contact. Can you see the organization? Organizing committee. Now it would be interesting to look at the references and whether they explicitly reference someone on this. I mean, you cannot know, but Adam Santol. Tara Sainath. Maybe they didn't. Program committee. George Dahl, I guess Oh yeah, here's a George Dahl. George E. Dahl, which is here. Okay, whatever. It's not really relevant. All right, so I wonder why they Freeman. Why did they cite this? I don't really understand this. Guide to Theory of NP Completeness. This looks like a citation that's just in there because someone was sitting on the committee. So, but I don't know. Gary. Maybe I'm wrong with this. Probably I'm wrong. But okay. Okay, but of course it's a pretty high profile conference, so whatever. Oh no, I was trying to read through the paper, through the references. Okay, then we have the paper we read yesterday, Neural Message Passing for Quantum Chemistry, an ICML, Inductive Representation Learning on Large Graphs, Representation Learning on Graphs, Methods and Applications, Approximation Capabilities of Multi-Layer Feed-Forward Networks. Multi-layer feed-forward networks are universal approximators. Batch normalization, accelerating deep learning, deep network training by reducing internal covariate shift. Anomalous work embeddings, molecular graph convolutions, method for stochastic optimization. This is the Adam paper. Semi-supervised classification with graph convolution networks, also ICLR. Learning convolutional neural networks, deep learning on point sets for 3D classification and segmentation. Simple neural network module for relational reasoning. Measuring abstract reasoning, computational capabilities of graph neural networks, the graph neural network model, dropout paper, graph attention networks. Okay, they already cited this here. So the graph attention was prior to this. I wonder in which context they cite it. So Peter Velikovic. coverage. There are other non-standard neighbor aggregation schemes that we do not cover. Example given, average via attention. We emphasize that our theoretical framework is general enough to characterize the representational power of any aggregation-based GNNs. In the future, it would be interesting to apply our framework to analyze and understand our aggregation scheme. Okay. Okay, it's just here. Okay. Then they have graph capsule, a reduction of a graph to a canonical form, a representation learning on graphs with jumping knowledge networks, whatever. Hierarchical graph representation learning with differentiable pooling, deep sets, an end-to-end deep learning architecture for graph classification. Okay, and then they have their proof. Good. Something about the data set, and that's it. So let's start to read on a second pass. Okay, let's start reading the preliminaries. Okay, we begin by summarizing some of the most common GNN models, and along the way, introduce our notation. Wait a second. So, okay. Let G is equal to the tuple of V and D, denote a graph with node feature vectors xv for V element V. So the small v is probably a vertex in the set of vertices in the graph, and the big E is the set of edges. There are two tasks of interest. One, node classification, where each node V in V, small v in big V, has an associated label Y sub V, and the goal is to learn a representation vector HV of V such that V's label can be predicted as YV is equal to f of HV. What this means is, okay, for each node in the graph, V1, V2, V3, we will have a hidden state. So V1 has HV1, V2 has HV2, and this is just V3 has HV3, and this is a vector. This is a vector, this is a vector, this is a vector, vectors. And F is just something like a ReLU with an MLP. And this we apply on all of these, and then we get Y. Okay. Not a ReLU, but probably a sigmoid. So this is probably something like a sigmoid of MLP of HV, right? Or something like that. And the second task, so this is different, graph classification. So while this is doing it on each of the individual nodes so node classification and graph classification. So here we apply the function to each of the individual ones, and here we just applied once to the aggregate of them. So this needs an aggregation of all nodes, which makes sense. So 2, graph classification, where given a set of graphs G1 to Gn, element the set of graphs and their labels Y1 to Yn, which is part of the label set, we aim to learn a representation vector Hg that helps predict the label of an entire graph. We aggregate the nodes, we apply a function to that. So we aggregate the nodes, this we call then Hg, and we process this graph embedding through a function to get the output. Graph neural networks. GNNs use the graph structure and node features xv to learn a representation vector of a node hv or the entire graph hg. Modern GNNs follow a neighborhood aggregation strategy where we iteratively update the representation of a node by aggregating representations of its neighbors. After k iterations of aggregation, a node's representation captures the structural information within its k-hop network neighborhood. Formally, the kth layer of a GNN is we combine. What is HU? Okay. Combine HVK-1 with AVK. AVK is the aggregate of all of the neighbors of V, of all of the neighbors of V, of all of their hidden states, which is then used as a message. They call it the aggregate. In the previous paper, they called it the message, which is then used to update the hidden state of the vertex. Where HVK is the feature vector of node V at the kth iteration layer, we initialize HV0 to XV, and the neighborhood of V is a set of nodes adjacent to V. The choice of aggregate K and combine K in GNNs is crucial. A number of architectures for aggregate have been proposed. In the pooling variant of GraphSage, aggregate has been formulated as this. It's a ReLU of this matrix multiply and max pooling of all of the nodes, of all of the neighborhood nodes, where W is a learnable matrix and max represents an element-wise max pooling. Okay, element-wise max pooling. The combined step could be a concatenation followed by a linear mapping, as in GraphSage. In graph convolutional networks GCN, the element-wise mean pooling is used instead. And the aggregate and combined steps are integrated as follows. So we take the mean of all of the hidden states of the neighborhood and together with V itself. And we take their hidden state, we get the mean, we make a matrix multiply and the ReLU. Many other GNNs can be represented similarly to equation 2.1. For node classification, the node representation HVK, big K. Why do they use a big K now? For each vertex in the graph, is used for prediction. For graph classification, the readout function aggregates node features from the final iteration to obtain the entire graph's representation Hg. So readout can be a simple permutation invariant function such as summation or more sophisticated graph level pooling function. Okay. Weisfeiler-Lehmann test. The graph isomorphism problem asks whether two graphs are topologically identical. So topologically identical is the right term. This is a challenging problem. No polynomial time algorithm is known for it yet. Apart from some corner cases, the Weisfeiler-Lehmann test of graph isomorphism is an effective and computationally efficient test that distinguishes a broad class of graphs. Its one-dimensional form, naive vertex refinement, is analogous to neighbor aggregation in GNNs. The Weisfeiler-Lehmann test iteratively 1. Aggregates the labels of nodes and their neighborhoods, and 2. Hashes the aggregate labels into unique new labels. Hashes the aggregate labels. Okay. The algorithm decides that two graphs are non-isomorphic if at some iteration the labels of the nodes between the two graphs differ. Based on the Weisfeiler-Lehmann test, Shervashidze et al. Proposed the WL subtree kernel that measures the similarity between graphs. The kernel uses the counts of node labels at different iterations of the WL test as a feature vector of the graph. Intuitively, a node's label at the kth iteration of WL test represents a subtree structure of height k rooted at the node. Thus, the graph features considered by the WL subtree kernel are essentially counts of different rooted subtrees in the graph. So I don't really know how this test works. Basically, you assign labels to vertices, and then you see, yeah. So this is obviously not enough to understand what the test is actually doing, but that's okay. All right, so now they introduce their theoretical framework for assessing the representative power of a graph. A rooted subtree. Okay, wait a second. Did they already reference figure 1? Okay. Intuitively, a node label at the kth iteration of WL test represents a subtree structure of height k rooted at the node. Thus, the graph feature is considered by the... Okay. 2 WL iterations. So this aggregates from this and this, and from this and this. This and this and this and this, probably. This is not really... And the multi-set here is just, we have three green dots that all map to, that all are connected with the blue dot. Is that true? Okay, because they are the same. Let's see. Theoretical framework overview. We start with an overview of our framework for analyzing the expressive power of GNNs. Figure 1 illustrates our idea. A GNN recursively updates each... Okay, let's actually read an overview of our theoretical framework. Middle panel. Rooted subtree structures at the blue node that the WL test uses to distinguish different graphs. Right panel. If a GNN's aggregation function captures the full multi-set of node neighbors, the GNN can capture the rooted subtrees in a recursive manner and be as powerful as the WL test. If a GNN's aggregation function captures the full multi-set of node neighbors, it can capture the rooted subtree. The rooted subtree. Okay, I don't really understand what the rooted subtree here is. What that really means. We'll see. Throughout the paper, we assume node input features are from a countable universe. Okay. For finite graphs, node feature vectors at deeper layers of any fixed model are also from a countable universe. What the heck do they mean by a countable universe? Okay, I have no idea why they say it's from a countable universe, but okay. So finite graphs, a finite set of vertices, okay. Makes sense. For notational simplicity, we can assign each feature vector a unique label in ABC, in the set ABC, okay? Then feature vectors of a set of neighboring nodes form a multiset. Then feature vectors of a set of neighboring nodes form a multiset. The same element can appear multiple times since different nodes can have identical feature vectors. This makes sense. Okay, definition 1. Multiset. A multiset is a generalized concept of a set that allows multiple instances for its elements. More formally, a multiset is a two-tuple XSM where S is the underlying set of X that is formed from its distinct elements, and M gives the multiplicity of the elements, so how many of them are in the set. To study the representational power of a GNN, we analyze when a GNN maps two nodes to the same location in the embedding space. Intuitively, a maximally powerful GNN maps two nodes to the same location only if they have identical subtree structures with identical features on the corresponding nodes. Okay, what they probably mean by that is we have a V1, and let's say V1 is connected to this neighborhood. So the neighborhood of V1 is the set of V2, V3, and V4. If the GNN processes this graph, it only creates this vector or this output if this subtree structure is the same. And another subtree structure where we have, for example, V4 or V5 as well in here, that leads to a different output. Okay, so the ability, the expressive framework measures how well the GNN separates two topologically different graphs. Okay. Since subtree structures are defined recursively, via node neighborhoods, we can reduce our analysis to the question whether a GNN maps two neighborhoods, i.e. two multisets, to the same embedding or representation. Analysis to the question whether a GNN maps two neighborhoods, i.e. two multisets, to the same embedding or representation. Okay. i.e. multisets, no. A maximally powerful GNN would never map two different neighborhoods, i.e. multisets of feature vectors, to the same representation. This means its aggregation scheme must be injective. Thus, we abstract a GNN's aggregation scheme as a class of functions over multisets that their neural network can represent, and analyze whether they are able to represent injective multiset functions. Okay, so only if the multiset is the same of the neighborhood for a node, it should produce the same output. So this means injective. Next, we use this reasoning to develop a maximally powerful GNN. In section 5, we study popular GNN variants and see that their aggregation schemes are inherently not injective and thus less powerful, but that they can capture other interesting properties of graphs. Okay. Section 4. Building powerful graph neural networks. Okay, I will quickly grab something to drink and then come back. All right. All right, building powerful graph neural networks. First, we characterize the maximum representational capacity of a general class of GNN-based models. Ideally, a maximally powerful GNN could distinguish different graph structures by mapping them to different representations in the embedding space. Okay. This ability to map any two different graphs to different embeddings, however, implies solving a challenging graph isomorphism problem. That is, we want isomorphic graphs to be mapped to the same representation and non-isomorphic ones to different representations. In our analysis, we characterize the representational capacity of GNNs via a slightly weaker criterion, a powerful heuristic called Weisweiler-Lehmann graph isomorphism test. that is known to work well in general, with a few exceptions. Example given regular graphs. Lemma 2. Where's lemma 1? Okay. Let G1 and G2 be any two non-isomorphic graphs. If a graph neural network that maps a graph to a d-dimensional real-valued vector maps G1 and G2 to different embeddings, the Weisfeiler-Lehmann graph isomorphism test also decides G1 and G2 are non-isomorphic. Proofs of all lemmas and theorems can be found in the appendix. Hence, any aggregation-based GNN is at most as powerful as the WL test in distinguishing different graphs. A natural follow-up question is whether there exist GNNs that are in principle as powerful as the WL test. Our answer in theorem 3 is yes. If the neighbor aggregation and graph level readout functions are injective, then resulting GNN is as powerful as the WL test. Theorem 3, let G that maps a graph to a real valued vector be a GNN with a sufficient number of GNN layers. A maps any graphs G1 and G2 that the Weisfeiler-Lehmann test of isomorphism decides as non-isomorphic to different embeddings if the following conditions hold. Let's skip over this. A aggregates and updates node features iteratively with this function, where the functions f, which operates on multisets, and phi are injective. And the readout, which operates on the multiset of node features, is injective. We prove this, blah, blah, blah. Lemma 4. Assume the input feature space x is countable. Let gk be the function parameterized by GNN's kth layer for k is equal to 1 to L, where G1 is defined on multisets of bounded size, blah, blah, blah. The space of node hidden features is also countable for all this. Okay, not really interesting for now. We can look at it later. Here it is also worth discussing an important benefit of GNNs beyond distinguishing different graphs, that is capturing similarity of graph structures. Note that node feature vectors in the WL test are essentially one-hot encodings. Node feature vectors. One-hot encodings thus cannot capture the similarity between subtrees. Okay, this I didn't really understand. Okay. But this probably also comes from not understanding the WL test. Question mark. In contrast, a GNN satisfying the criteria in Theorem 3 generalizes the WL test by learning to embed the subtrees in low-dimensional space. This enables GNNs to not only discriminate different structures, but also to learn to map similar graph structures to similar embeddings and capture dependencies between graph structures. Capturing structural similarity of the node labels is shown to be helpful for generalization, particularly when the co-occurrence of subtrees is sparse across different graphs or there are noisy edges and node features. Okay, now they introduce their graph isomorphism network. So they say, okay, we have the aggregate function. We have the combine function. I think they okay, the aggregate function, this is what they called message function in the paper we read yesterday, which aggregates the embeddings of all of the nodes they are in the neighborhood, and the combine function they called the vertex update function. Okay, and they said these should be injective, and also the readout. They should all be injective. And if that is true, if they are injective, then we can follow that the GNN is as good as WL test. Which is not perfect because there are some exceptions where it cannot detect isomorphism correctly. Almost detect isomorphism with exceptions. Right? This is their argument. Without really knowing what the WL test is, but we should probably try to understand it if we want to fully understand how they prove this. Okay, so the subtree is basically, okay, this blue dot, I think this is the way. This blue dot is connected to these 3 green dots, right? And then this green dot is connected to this blue dot and this green dot. But why does it have... Oh yeah, so I think, okay, this green dot now is connected to this green dot, and this blue dot. So this has these 3 connections. This green dot is only connected to the blue dot and the green dot down below. So this is this, and the last one is this. So this is the rooted subtree. And if we would roll it out once more, it would just be recursive, right? What exactly this rooted subtree now is doing is a good question. Which is probably answered if we would know what the WL test does. But okay, let's just try to further go through the paper and understand what their network is doing. So probably they will now define injective functions for the aggregate, for the combine function, and for the readout function. Okay. Having developed conditions for a maximally powerful GNN, we next develop a simple architecture graph isomorphism network that provably satisfies the conditions in Theorem 3. This model generalizes the WL test and hence achieves maximum discriminative power among GNNs. To model injective multiset functions, okay, again, a multiset is just, we can have different vertices that have the same representation or multiple of these. Yeah. And if we have 2 different multisets, the GNN should also have 2 different outputs. And the multiset is always a neighborhood, right? Or a set of neighborhoods? I don't know. Okay. To model injective multiset functions for the neighbor aggregation, we develop a theory of deep multisets. Okay. i.e. parameterizing universal multiset functions with a neural network. With neural networks. Parameterizing universal multiset functions. Okay. Our next lemma states that some aggregators can represent injective, in fact, universal functions over multisets. What is a universal function? Universal Okay, a function that can imitate on. Okay. Assume x is countable. There exists a function f that maps x. I think x is the set of nodes, right? Or is this the set of, is this the set of neighborhoods? Okay, so that we get the sum over f of x. So, okay, this is a specific neighborhood probably. This is the set of all neighborhoods. And we sum for each neighborhood all of the individual representations together. Okay. Moreover, any multiset function g can be decomposed as g of x is equal to phi of the sum over blah 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 for some function phi. We prove lemma 5 in the appendix. The proof extends the setting from sets to multisets. An important distinction between deep multisets and sets is that certain popular injective set functions, such as the mean aggregator, are not injective multiset functions. With the mechanism for modeling universal multiset functions lemma 5 as a building block, we can conceive aggregation schemes that can represent universal functions over a node and the multiset of its neighbors, and thus will satisfy the injectiveness condition A in theory, blah. Rollerith 6. Let's not look at this for now. We can use multilayer perceptrons to model and learn F and yeah, I don't really know what that is. Thanks to the universal approximation theorem. Okay, in practice we model this with one MLP because MLPs can represent the composition of functions. In the first iteration we do not need MLPs before summation if input features are one-hot encodings, as the summation alone is injective. We do not need MLPs. In the first iteration, we can make eta a learnable parameter or fixed scalar. Then giant updates, such as node representations, are. Okay, let's look at this formula. Okay. So we look at the node V, a vertex V. We have a representation at the first iteration, for example. And we take this and we add it with a discounting factor or whatever. To this, we add all of the representations of the nodes from the previous iteration that are in the neighborhood of our vertex. Makes sense. Generally, there may exist many other powerful GNNs. GIN or GIN, I don't know, let's call it GIN. GIN is one such example among many maximally powerful GNNs while being simple. Graph level readout of GIN. Node embeddings learned by GIN can be directly used for tasks like node classification and link prediction. For graph classification tasks, we propose the following readout function that, given embeddings of individual nodes, produces the embedding of the entire graph. Okay. Sorry. An important aspect of the graph level readout is that node representations corresponding to subtree structures get more refined and global as the number of iterations increases. Of course, because if you increase the number of iterations, the tree gets larger and more recursive, and right? All of the nodes get to talk to each other. Yet features from earlier iterations may sometimes generalize better. To consider all structural information, we use information from all depths iterations of the model. We achieve this by an architecture similar to jumping knowledge networks, where we replace equation 2.4 with graph representations concatenated across all iterations. Oh, they concatenate over all iterations. What does that readout? Okay. Let's look at the figures here. Figure 2. So input, sum minus multiset, mean distribution, max set. Ranking by expressive power for sum, mean, and max aggregators over a multiset. The left panel shows the input multiset, i.e. the network neighborhood to be aggregated. Okay, this is one neighborhood. The next 3 panels illustrate the aspects of the multiset a given aggregator is able to capture. Sum captures the full multiset. Mean captures the proportion distribution of elements of a given type. Okay, so we have two red, we have 4 blue. So what's this thing can capture? Only the ratio between red to blue. Okay. And the max aggregator ignores multiplicities, reduces the multiset to a simple set. Okay, so we apply max over different types. Yeah, so max only decides between the two. I don't know. Okay, and now figure 3, examples of graph structures that mean and max aggregators fail to distinguish. So this is now interesting. So between the two graphs, nodes V and V prime get the same embedding even though their corresponding graph structures differ. So this is exactly what they're trying to avoid, right? You have 2 graphs with a different topology, with a different structure, and they get the same embedding. This they want to really not have. But this is the problem with, so the sum, let's say blue has the value 5. So sum would look at this and at this. They have 5 plus 5 is 10. Here, the sum aggregator would look at this, at this, at this, and it would be 5 plus 5 plus 5 is equal to 15. So they are different. They're not equal. However, the mean thing would look at 5 and 5 produce a 5. And here, 5, 5, 5 would produce a 5. They are the same, which is a problem because the structure is different. And this is true for max as well. And here max will also always fail because it will only consider the difference between between the different types. And if we have two of them or multiple of them, then it will fail. So the key thing they do here is they look at multisets. This is their key thing. So they essentially ask the question, what happens if I have multiple nodes that have the same representation? This is the main question they ask. Okay. By theorem 3 and corollary 6, if GIN replaces readout in equation 4.2 with summing all node features from the same iterations. So the readout would be the sum over all node features from the same iterations. We do not need an extra MLP before summation for the same reason as in equation 4.1. You don't need before summation. It probably generalizes the WL test and the WL subtree kernel. Okay? Less powerful but still interesting GNNs. Next, we study GNNs that do not satisfy the conditions in theorem 3, including GCN and graph stage. We conduct ablation studies on two aspects of the aggregator in equation 4.1, one-layer perceptrons instead of MLPs, and two mean or max pooling instead of the sum. We will see that these GNN variants get confused by surprisingly simple graphs and are less powerful than the WL test. Nonetheless, models with mean aggregators like GCN perform well for node classification tasks. To better understand this, we precisely characterize what different GNN variants can and cannot capture about a graph and discuss the implications for learning with graphs. So depending on what layers you use, whether you use a one-layer perceptron in the aggregator function, this can mean that your architecture may struggle with certain things. Good. One-layer perceptrons are not sufficient. The function f in lemma 5 helps map distinct multisets to unique embeddings. It can be parameterized by an MLP by the universal approximation theorem. Nonetheless, many existing GNNs instead use a one-layer perceptron. This, the combination of a sigmoid and a matrix multiply, probably a linear mapping followed by a nonlinear activation function, such as relu. Such one-layer mappings are examples of generalized linear models. Therefore, we are interested in understanding whether one-layer perceptrons are enough for graph learning. Lemma 7 suggests that there are indeed network neighborhoods, multisets that models with one-layer perceptrons can never distinguish. There exists finite multisets X where X1 and X2 are not the same, so that for any linear mapping W, they map to the same. The main idea of the proof for lemma 7 is that one-layer perceptrons can behave much like linear mappings, so the GNN layers degenerate into simply summing over neighborhood features. Our proof builds on the fact that the bias term is lacking in the linear mapping. With the bias term and sufficiently large output dimensionality, one-layer perceptrons might be able to distinguish between multisets. Nonetheless, unlike models using MLPs, the one-layer perceptron, even with the bias term, is not a universal approximator of multiset functions. Consequently, even if GNNs with one-layer perceptrons can embed different graphs to different locations to some degree. Such embeddings may not adequately capture structural similarity and can be difficult for simple classifiers, example given, linear classifiers to fit. In section 7, we will empirically see that GNNs with one-layer perceptrons, when applied to graph classification, sometimes severely underfit training data and often perform worse than GNNs with MLPs in terms of test accuracy. Structures that confuse mean and max pooling. What happens if we replace the sum in h of x is equal to the sum with this function with mean or max pooling as in GCN or GraphSage? Mean and max pooling aggregators are still well-defined multiset functions because they are permutation invariant, but they are not injective. Figure 2 ranks the three aggregators by their representational power. So what does permutation invariant mean? So if the nodes are just in a different order, they will still produce the same output. This is true for mean and max, but what is not true is what we see, that they are injective, which they show by this figure here, which is a very nice figure. Figure 2 ranks the three aggregators by their representational power, and Figure 3 illustrates pairs of structures that the mean and max pooling aggregators fail to distinguish, which is what we looked at previously. Here, node colors denote different node features, and we assume the GNNs aggregate neighbors first before combining them with the central node labeled as V and V prime. In Figure 3a, every node has the same feature A, and f of A is the same across all nodes for any function f. So the blue dot always produces the same embedding, essentially, and they are different from the green and the red. Thus, in this case, mean and max pooling aggregators fail to capture any structural information. We saw this. In contrast, the sum aggregator distinguishes, wait a second. So in contrast, the sum aggregator distinguishes the structures because 2 times f of a and 3 times f of a give different values. Yeah, this is what I was explaining. And Figure 3 suggests that mean and max have trouble distinguishing graphs with nodes that have repeating features. Let H color, R for red, G for green, denote node. We saw this. Mean learns distributions. To characterize the class of multisets that the mean aggregator can distinguish, consider the example x1 is equal to s and m, x2 is equal to s and k times m, where x1 and x2 have the same set of distinct elements, but x2 contains k copies of each element of x1. Any mean aggregator maps x1 and x2 to the same embedding because it simply takes average over individual element features. Thus, the mean captures the distribution of elements in a multiset, but not the exact multiset, because there are many more in the second one. Yeah. Okay, max pooling, this is the same thing. It deduplicates basically. Remarks on other aggregators. There are other non-standard neighbor aggregation schemes that we do not cover. Example given, weighted average via attention and LSTM pooling. We emphasize that our theoretical framework is general enough to characterize the representational power of any aggregation-based GNNs. So their theoretical framework is looking at multisets and how well a given architecture can distinguish between different multisets. In the future, it would be interesting to apply our framework to analyze and understand other aggregation schemes. Other related work. Despite the empirical success of GNNs, there has been relatively little work that mathematically studies their properties. An exception to this is the work of Scarselli et al., who shows that the perhaps earliest GNN model can approximate measurable functions in probability. Li et al. Li et al. Show that their proposed architecture lies in the RKHS of graph kernels. But do not study explicitly which graphs you can distinguish. Each of these works focuses on a specific architecture and do not easily generalize to multiple architectures. In contrast, our results above provide a general framework for analyzing and characterizing the expressive power of a broad class of GNNs. Recently, many GNN-based architectures have been proposed, including some aggregation and MLP encoding, and most without theoretical derivation. In contrast to many prior GNN architectures, our graph isomorphism network, GIN, is theoretically motivated, simple, yet powerful. Great. So they show by using injective functions in the aggregate, in the combine function, and in the readout function, this thing is as powerful as the Weis-Feller-Lehmann test. Maybe. And therefore, they are almost graph isomorphism invariant. Experiments. We evaluate and compare the training and test performance of GIN and less powerful GNN variants. Training set performance allows us to compare different GNN models based on their representational power, and test set performance quantifies generalization ability. Datasets. We use 9 graph classification benchmarks, 4 bioinformatics datasets, MUTAG, PTC, blah blah blah, and 5 social network datasets. Reddit, Multi, 5K. Importantly, our goal here is not to allow the models to rely on the input node features, but mainly learn from the network structure. Because this is always the case, if you also have to do extensive feature engineering on the nodes, then you kind of run into the same problem that the neural message passing network was trying to avoid. So we still need feature engineering on the node level. And what about edge features? So they only talk about vertices. They only talk about vertices here. What about the edge features? Okay. Importantly, our goal here is not to allow the models to rely on the input node features, but mainly learn them from the network structure. Thus, in bioinformatic graphs, the nodes have categorical input features, but in the social networks, they have no features. For social networks, we created node features as follows. For the Reddit dataset, we set all node feature vectors to be the same. Thus, features here are uninformative. For the other social graphs, we use 100 encodings of node degrees. What is a node degree graphs? In graph theory, measures a node's connectivity by counting its adjacent edges. Okay, how well it is basically connected. For the other social graphs, we use 100 encodings of node degrees. Dataset statistics are summarized in Table 1, and more details of the data can be found in Appendix 1. Models and configurations. We evaluate GIN's equations 4.1 and 4.2. Let's look at them again. So 4.1, this is the aggregation and combination. And 4.2 readout. Yeah, they never really defined readout. Do they? What are you reading? I am reading a paper on graph neural networks. Yesterday I was reading a paper that was a work that was prior to this, and now I am reading this one, which tackles the topic of graph isomorphic networks. So a graph neural network that maps two graphs that are topological or structurally the same to the same output. And if the graph has a different structure, it should map it to different outputs. And then you can learn something about graphs, like whatever. We could look at the data sets then in detail, but yeah. Okay. Importantly, our goal here is not to allow the models to rely on the input node features, but mainly learn from the net. Okay, we already read that. Under the GIN framework, we consider two variants: a GIN that learns eta in equation 4.1 by gradient descent, which we call GIN eta, and two, a simpler, slightly less powerful GIN where eta in equation 4.1 is fixed to 0, which we call GIN 0. As we will see, GIN 0 shows strong empirical performance. Not only does GIN 0 fit training data equally well as GIN eta, it also demonstrates good generalization, slightly but consistently outperforming GIN eta in terms of test accuracy. For the less powerful GNN variants, we consider architectures that replace the sum in the GIN 0 aggregation with mean or max pooling, or replace MLPs with one layer perceptrons, i.e. linear mapping followed by ReLU. Okay, they also have the code here. That might be worth looking at. Oops, not found. Let's look at the Wayback Machine. Oh, that would be too bad. Copy link. Oh, I have a dot in here. Why did they delete this? Here it is. Unable to load page. No. Oh, that's too bad. They updated this also, right? Or did they? Maybe we can find it. What? Here it is, powerful GNNs. They didn't remove it. Graph CNN. Main.py. Yeah, we can look at this. All right, so let's look at the chart. This is training accuracy. Training accuracy on different. Oh no. Okay, so we see WL subtree kernel. Some MLP Gen 1, Gen 0. Okay. Mean one layer. Mean MLP. So we see that the mean aggregation seems to not be very good. And the sum. Where's the green line here? Can't even see it. Okay. In figure 4 in table 1, a model is named by the aggregator perceptron it uses. Here, mean one layer and max one layer correspond to GCN and GraphSage, respectively, up to minor architecture modifications. We apply the same graph level readout in equation 4.2 for GINs and all the GNN variants. Specifically, some readout on bioinformatics dataset and mean readout on social datasets due to better test performance. Okay, following this, we perform tenfold cross-validation with libsvm. We report the average and standard like this. We report where was it? We report the average and standard deviation of validation accuracies across the 10 folds within the cross-validation. Okay, for all configurations, 5 GNN layers, including the input layer, are applied, and all MLPs have 2 layers. Batch normalization is applied on every hidden layer. We use the Atom optimizer with initial learning rate and decay the learning rate by 0.5 every 50 epochs. The hyperparameters we tune for each dataset are 1. The number of hidden units for bioinformatics graphs and 64 for social graphs. So this is basically the embedding space of the nodes or the vertices. The batch size, the dropout ratio, after the dense layer, the number of epochs, single epoch with the best cross-validation accuracy averaged over the 10 folds was selected. Note that due to the small dataset sizes, an alternative setting where hyperparameter selection is done using a validation set is extremely unstable. Okay. Example given from Mutag, the validation set only contains 18 data. Yeah, of course. If your validation set only has the 18 data points, of course, your early stopping or whatever is very unstable. We also report the training accuracy of different GNNs, where all the hyperparameters were fixed across datasets. 5 GNN layers, including the input layer, hidden units of size 64, mini batch of size 128, and 0.5 dropout ratio. For comparison, the training accuracy of the WL subtree kernel is reported. So they do. I don't really understand how they do the WL subtree kernel though. The WL subtree kernel. So how do they do the WL subtree kernel? So they said that the WL subtree basically corresponds to a 1-hot encoded vector at an iteration. So let's search for this. 1-hot that node feature vectors in the WL tests are essentially one-hot encodings and thus cannot capture the similarity between subtrees. And do they use these one-hot encodings then and put an SVM on this? Support vector machine? Big question mark here. With a number of state-of-the-art baseline for graph classification, the WL subtree kernel, so this is something we probably should read, where CSVM was used as a classifier, the hyperparameters we tune are C, let's use Scherwa-Schietze. Oh, they're from Germany. Let's put this into my database for reading. So this will be something we should read probably in the future. Of course. Let's copy this link. Shit. Oh, was the PDF? Oh, whatever. Okay, so let's continue. Where is my OBS? Here. Let's close this. Let's go here. Okay. We use as a classifier the hyperparameters we tune our C of the SVM and the number of WL iterations. State-of-the-art deep learning architectures, the diffusion convolutional neural networks, Apache SAN, and deep graph CNN, anonymous walk embeddings for the deep learning methods, and AWL. We report the accuracies reported in the original papers. Okay, so they didn't implement this. They just copied from the original papers. All right. Results, training set performance. We validate our theoretical analysis of the representational power of GNNs by comparing their training accuracies. Models with higher representational power should have higher training set accuracy. Figure 4 shows training curves of GINs and less powerful GNN variants with the same hyperparameter settings. First, both the theoretically most powerful GNN, i.e. GIN eta and GIN 0, are able to almost perfectly fit all the training sets. In our experiments, explicit learning of eta and GIN eta yields no gain in fitting training data compared to fixing eta to 0 as in GIN 0. In comparison, the GNN variants using mean max pooling or one-layer perceptrons severely underfit on many datasets. In particular, the training accuracy patterns align with our ranking by the model's representational power. GNN variants with MLPs tend to have higher training accuracies than those with one-layer perceptrons. And GNNs with some aggregators tend to fit the training sets better than those. So, okay, one-layer perceptron Okay, they have a single layer and multiple layers, of course. Okay. Yeah. On our datasets, training accuracies of the GNNs never exceed those of the WL subtree kernel. Wait, let me, for short. Let me see again what they, okay. They applied the MLP on the aggregation. We will look at the table in a second. Okay. On our datasets, training accuracies of the GNNs never exceed those of the WL subtree kernel. This is expected because GNNs generally have lower discriminative power than the WL test. For example, on IMDb binary, none of the models can perfectly fit the training set, and the GNNs achieve at most the same training accuracy as the WL kernel. This pattern aligns with our result that the WL test provides an upper bound for the representational capacity of the aggregation-based GNNs. However, the WL kernel is not able to learn how to combine node features, which might be quite informative for a given prediction task, as we will see next. So test set performance. I mean, training set performance. I don't even know why they measure this. I mean, it's interesting that, okay. Okay, so they seem to be, seems like their network is almost always better, except for the NCI1 and Mutag, where it's worse than the WL subtree. Okay. Did they implement this here maybe? EQDM. Models, graph CNN. Do they have maybe more branches? No. Util? S2V graph. Load data. Nah, I don't know. Okay, test set performance with strong expressive power that convert. Table 1 compares test accuracies of GINs, other GNN variants, as well as the state-of-the-art baselines. First, GINs, especially GIN 0, outperform or achieve comparable performance as the less powerful GNN variants on all 9 datasets, achieving state-of-the-art performance. GINs shine on the social network datasets, which contain a relatively large number of training graphs. For the Reddit datasets, all nodes share the same scalar as node features. Here, GINs and some aggregation GNNs accurately capture the graph structure and significantly outperform other models. This makes sense because when all nodes have the same representation, you need a summation because you cannot count with a mean. And this is probably also why they focused on this multi-set thing. Even if node degrees are provided as input features, mean-based GNNs perform much worse than sum-based GNNs. Makes sense on this Reddit thing. With mean MLP aggregation is 71.2 plus 4.6% on Reddit binary and 41.3 plus minus 2.1% on Reddit multi 5K. Comparing GINs, GIN 0 and GIN eta, we observe that GIN 0 slightly but consistently outperforms GIN eta, Since both models fit training data equally well, the better generalization of Gen 0 may be explained by its simplicity compared to Gen eta. Okay, yeah. Well, you have a different... You've tried that. It's okay. You don't have to always mention it. But okay. So, to summarize this paper, we have GNNs. We assessed we have many different variants of networks. We haven't looked at this from a theoretical perspective, what they can express in theory. We only went by trial and error. So what we now want to do is look at the architecture and deduce from the architecture what the model can theoretically express. And they do so by looking at multi-sets. So sets with different vertices from the graph, but the vertices can have the same representation. And they show that different aggregations, for example, cannot distinguish between two multisets. And if a graph neural network cannot distinguish between two multisets that are different, its representation power is lower. And then they also have a proof here, we would have to go through this, that if the three functions of the graph neural network, the aggregation function, which is the message function from the previous paper, the vertex update function, and the readout function are injective. That is, if the inputs to the function are the same, the outputs are also the same, is that true? Yeah. Then the GNN is as good as the Weisfeiler-Lehmann test. And the Weisfeiler-Lehmann test tests whether two graphs are isomorphic. That is, whether their structure is the same. And this is also not a perfect test, as it seems. So they call their graph neural network graph isomorphism networks because their networks handle more or less isomorphic graphs the same. Yeah, and that's basically it. Maybe let's, for the last few minutes, look at their code. At their model. Okay, let's look at the forward pass. Oh my goodness. Okay, batch graph. So for each graph in the batch graph, we concatenate the node features. Pre-processed graph pool. Okay. Some AVE pool. Batch graph. It's actually not that long, the forward method. Okay, so for each layer, which is probably the number of iterations, right? Next layer. Oh my goodness. Okay. So okay, next layer, apps. Next layer. SPMM. So this is sparse matrix multiply, right? I think this is sparse matrix multiply because the adjacency block is multiplied with H. This is probably the summation. So this matrix multiply probably does the aggregation across the neighborhood. Representation of neighboring and center nodes. We then apply an MLP, which is exactly this formula we had. We then do a batch norm and we apply a ReLU. And we do this padded neighbor list. Okay, padded neighbor list. They need this for the max pooling, okay? I think this is, if you were to, of course, I would probably not be able to implement this right now, but out of my head, but if we would take some time, we would probably get this to work, which we will maybe do in a future stream. So the last paper from the series I want to read is called Strategies for Pre-Training Graph Neural Networks, because this one will now add to the this cites this paper that we read, and it will add edge features to the graph isomorphism networks. And we probably want edge features to describe the relationship between vertices. So this will be the last read, and okay, so it has 8, has a bunch of pages for the appendix. Okay, so this is coming also from Stanford, Howard, and the University of Iowa. All right, then, guys, I wish you a nice and sunny afternoon, and yeah, I'll see you on the next one.